So we're still looking at applications for derivatives, multivariable functions. 12 and then 13, we're going to do something else. And then finally, no, 13, I think we're going to start talking about double integrals next class. But in any case, our task today is going to be to figure out something called the Lagrange multiplier. And basically what we're doing here is we're doing constrained, or we're finding constrained mins and maxes of functions. So last day we looked at how we can find the min and or max or saddle points of multivariable functions by using the first and second derivatives, right? First derivatives, you set it equal to 0, you get a critical point. You now look at those critical, you take the second partial derivatives, and they allow you to do what we call the second derivative test, which then allows you to figure out if those critical points, if at those critical points, the function is a minimum or a maximum or a saddle point, okay? Now what we're going to do is we're going to do the same thing, but we're going to add what we call a constraint, okay? Which means we're not going to find the absolute min or max of some function, okay? We're going to find the min or max of that function when we constrain, for instance, two variables, x and y, to follow some other equation, okay? And why would we want to do this? Well, let's look at a quick example. For instance, a very simple example where we've got a field, and we want to fence this field, okay? The field has a width and it has a length. And we want to fence this field, and we are told that the field has an area of 1,200 meters squared. Or the field needs to have an area of 1,200 meters squared is probably the way I should say it. Okay, there's a street on one side of this field, and we are told that the fencing for that side of the field costs $50 a meter. So on this side of the field, the fence costs $50 a meter. For the other three edges, because they're not facing the street, we only need fencing that costs $30 a meter. Okay, so for three edges of this field, we got a fence at $30 a meter. For the side of the field that faces the road, we got to use more expensive fence, $50 per meter. And we are asked, okay, we want to minimize the cost of the fencing. Okay, so if that's all I said to you, and let's say I didn't write this down yet. Can I still erase this? Yeah. If I said we've got some field there, and that's the cost of the fencing, tell me what should be the dimensions W and L of this field in order to minimize the cost of the fence. And this, let's say that what I've got on the screen, that's the only information you're given. What would you say? Well, you would be a smart aleck engineer and say, well, make W and L both equal to 0, your cost is 0, that's the minimum, right? Don't fence the field, right? That would be your minimum, right? If I gave you this as a final exam question, you'd all be rubbing your hands in glee going, yeah, I know the answer to that. Make W and L 0, that gives me my minimum cost, right? Well, obviously that doesn't make sense here. We got a field, and we're told that the area of the field has to be 1,200 meters squared. Okay, but they don't tell you whether it's a rectangle, whether it's a square. Okay, well, they tell you it has 4 sides, but other than that. So we've added a constraint. This is a constraint. If we're asked to minimize the cost of the fencing, we can't just make W and L equal to 0 because we're given a constraint. W and L can't be just any numbers. They have to be numbers such that 1,200 equals W times L, right? This is what we call our constraint equation. We can't just make W and L anything we want. W times L has to be equal to 1,200 meters squared. The area of the field, of the enclosed fenced field, has to be 1,200 meters squared. Okay, the objective though, is to minimize the cost. And what is the cost equal to? Well, the cost is going to be equal to 50 times L plus 2W times 30 plus 50 times 30, right? So the cost is equal to 50, no, I messed something up there, sorry. I messed something up there. I need more room here. 50 times L is this side. 2 times W times 30, and, 30 times L, not 50 times L. This is wrong. I need 30 times L for the cost of the fence on this edge. So that means we've got 80 L plus 60W. That's going to be the cost of the fencing, okay? And we want to minimize, this is what we call our objective function. It's the function we want to minimize. We want to find W and L such that cost C is minimized subject to the constraint that W times L has to equal 1200, okay? Again, obviously, without the constraint, I make W and L 0 and my cost is 0, which is the minimum, okay? That would be the minimum of this function. But subject to this constraint, W and L are not going to be equal to 0 because W times L have to be equal to 1200. Okay, so that's an example of an optimization problem subject to a constraint. So now we've got two functions to worry about. We've got our objective function. It's the function we're trying to minimize or maximize. And then we have our constraint function. Okay? All right, so how are we going to do this? Well, let me start with a different example and explain it to you abstractly before we look at the mathematics. Let's say that you are you're climbing a mountain, okay? And let's say that our mountain looks like this in the three-dimensional coordinate system. It's a perfect paraboloid. Okay, we've seen that thing a lot of times. So let's imagine that this is an actual hill that you're climbing or you're hiking on. And let's imagine that you don't actually, well, let's start with that. Let's say you climb to the top, okay? So you're climbing some switchbacks like this, and you finally get to the top, and then at the top, maybe you go down the other side, and you go down some switchbacks like this, okay? All right, I'm going to draw this in 2 dimensions now using level curves. X, Y, okay? The level curves for this for that surface, for that mountain, are going to look, they're circles. I know that's not a circle, but they look like this. That's better. Okay? So that would be the topographic map of that mountain, right? Those are the contour lines, lines of constant elevation or constant Z value. Okay, everybody with me so far? That gives me a contour plot of that function with level curves on it. Okay, now I'm going to plot my path. Well, I zigzagged up here, so I maybe did something like this, right? Then I got to the top, and then at the top, I went down some other switchbacks like this. Okay? Okay, without the path, though, if I asked you, where is the maximum of this function, of this hill? You would say, well, right here, right? That's the maximum. Okay? Now let me ask you, what would be the maximum of the hill where, if I'm constrained to being on this path? Where would the maximum be? Well, it'd still be right there, right? Okay. But now let's assume, I'm going to draw another one. I'm going to draw the same hill again. Well, I'm going to just draw the same, it's the same hill. I'm going to draw these again, my contour plot. But this time, I don't climb to the top. This time I go And I'm going to keep it a little bit simple. I start down here, and maybe this time I do this. I don't climb to the top. I sort of go part way, and then I go, I'm tired, I'm not going to go right to the top, and I start going down again. Okay? Now I ask you, what is the maximum terrain, what's the maximum height of that hill subject to the constraint of where I was going? So when I went up this hill, where did I reach a maximum? Okay, obviously it's not here anymore because I never went there. Okay? Is this the maximum? No? Tell me when to stop. Somebody yell when to stop. Right here? Back a little bit? Right about here? Not here?
No, in the back.
Okay, why are you saying here?
It's closest to the peak.
It's closest to the peak. Yeah, okay. What about the level curves? What are you noticing about when I'm here versus when I'm here? Compared to these level curves. And I could draw a bunch of other level curves. I could make draw as many concentric circles here of varying radius as I want, right? I've just shown you 4 of them. 1, 2, 3, 4, right? Let's use a different color. What if I drew this level curve? Then you would say, okay, I'm at the peak. I'm not at the peak. I'm at the maximum that I'm going to be right there, right? I'm not going to be at the max if I draw the one level curve just a little bit below that. Sorry, not very good. Okay, let's say the red one is at altitude above sea level of 500 meters, and the blue one is at 490. Okay? Well, is 490 my max? No. Because when you cross a level curve, you're actually still going up, right? Or going down. But this red one is magical because I don't cross it, I just touch it. Okay? So this is, my objection function is the hill. And I want to find the maximum point on the hill subject to a constraint. The constraint is the path that I follow when I hike. So it's the same thing as asking, what's the highest point I get to as I follow this path? Okay? So if I say, okay, remember this is x and this is y, if I say what's the maximum of that objective function, the hill, what values of x and y would you give me? You'd give me 0, 0, right? Right here. But if I ask you, what's the maximum point on the hill subject to this constraint? You're going to give me the x, y coordinates for this point right here, right? And you chose this point because it's right where you get just to the top and you start going down. And right when you get to this point here, when you get as high as you're going to get, you're not going up, you're not going down, right? You've just crested as high as you're going to get and you start going down again. That's going to be right where you touch one of these level curves. And you don't cross it, you get to it, and then you start going down. Okay? So that means mathematically what we're trying to do is we're trying to find this point. And what is special about the derivative of this function, df by ds, where ds is a distance along this path. What's special about df by ds right at this point? What's it equal to? 0. The slope is 0, right? Right when I get to this point here, I'm not going up, I'm not going down. The function isn't changing with respect to distance. The slope is 0, okay? So I'm looking for the point where df by ds is equal to 0. Okay, so let's just, any questions about that? Kind of makes sense? Okay, so let's go back to math. So in the general case, we've got in the xy plane, we've got some objective function, some multivariable function called f, and maybe one of the level curves like this, looks like this, maybe another one for it looks like this, okay? If you want to think of it as a hill again, you can, but just in general, those would be two level curves of some function f of x, y. So this is maybe f of x, y at a constant value equal to d2. Let's call this one f of x, y at a constant value of d1, okay? And what do we know about the gradient vector of f on any of these level curves? What is the gradient vector? Which way does it point? Inward, or maybe outward, depending on whether we're going up or down. But it's not pointing like this, right? That would be the tangent vector to that level curve. The gradient vector, we learned way back a long time ago when we talked about level curves, is always perpendicular to a level curve. So for this level curve, if I drew the gradient vector of f here, it would look either like this or like that. If I drew it over here for this level curve, it would look either like this or like that. Let's say inward. The gentleman up there said inward, so I'm just going to draw a bunch of gradient vectors for f. For that level curve, they'd look like that, right? And for this one, they'd look like this. They're perpendicular to the level curve. Okay, so that's our objective function, the thing we're trying to minimize or maximize. So now we've got this constraint function, okay? G is a function of x and y as well. Okay, well that means we can draw level curves for G as well. There's one particular level curve of G we're interested in, and that is our constraint function. If we go way back here to the fence, right? Here's our constraint function. This is G of W and L. It's equal to a constant. Typically, your constraint function is a function of multiple variables is equal to some number, a constant, okay? So that means one level curve of G of X, Y, or G of W, L in this example. So there's only really one level curve of G we're interested in, but there's lots of level curves of F, okay? Let's say that the level curve of G looks something like this. It could be anywhere, but let's say it looks like this. Okay, so this is G of x, y is equal to some constant C. That's our constraint. W times L is equal to 1200, for instance. Okay, well, we just said that the maximum value of F, which was the height on the mountain, subject to the constraint of the path we were following, is going to be at the point where this path just is tangent to one of the level curves of f, okay? And I've drawn that level curve here. Obviously the maximum or minimum. In this case, we might be looking for the minimum because the gradient vectors are pointing inward. Okay, obviously it's not here, right? Because if we keep going along G, f gets smaller. Smaller, smaller, smaller. Up, we reach the minimum value of f. If I keep going along here, f starts getting bigger again, right? This is the path. The constraint equation says I'm only allowed to have x, y values on this level curve. That's what the constraint equation means. Okay? So that means I'm looking for the point on this line where my function is maximum or minimum. Well, as long as I'm cutting across level curves of f, I haven't gotten to the max or the min yet. It's only when I get to a level curve and I just touch it tangentially and then I turn away from it again, that either must be the max or the min. Okay? Now, at that point, the gradient vector for f is going to look like that. Okay, so that's the gradient for f. What is the gradient for G going to look like? Well, it's also going to be always, the gradient vector of G is always perpendicular to a level curve of G. So at that same point, oh, I didn't draw that very well at all, did I? I'm going to do that again, sorry. My drawing isn't great. I'm going to draw it like, that doesn't look quite right either, but it's probably because of the way I drew the level curve for G. That's the gradient of f. Gradient of g is going to look like that. Okay, it's also perpendicular to its level curve. Doesn't really look like it here, but it is. Just imagine it is, okay? It's perpendicular to this, and this one is perpendicular to its level curve, okay? And since the two level curves are touching tangentially, what does that tell me about the relative directions of the gradient of f and the gradient of g? They're opposite, right? But they're parallel. Pointing in opposite directions, but they're parallel, right? This is a G. Okay, it means that the gradient vector of f and the gradient vector of g are going to be parallel to each other at the min-max point, which is defined by where the level curve of g just tangentially touches one of the level curves of f. Okay? How many level curves of f does g touch tangentially in the figure I drew? I've only drawn two level curves for f, but you could imagine an infinite number of level curves for f there, right? How many of them would g just tangentially touch?
One.
Just one, right? Right? Just like I showed you on the hill, I draw another level curve for f, just a little bit bigger or smaller than that small one there, and either g, the level curve for g wouldn't touch it at all, or it would cross it. And if g is still crossing level curves of f, that means it's still climbing the hill or it's still going down the hill. Okay, so there's only one, at least in a situation like this. Okay, so mathematically, what do we got then? Well, we've got, I didn't want to do that. Okay, I kind of skipped all of that. Maybe I should just write down. Okay, at that point, obviously, my function is not changing as I'm moving along that path G. That's what it means to be a max or a min. Okay, so, but the big thing here is these two gradient vectors at the point I'm looking for are parallel to each other, okay? Now, they could point in the same direction, they could point 180 degrees opposite directions, they could have the same magnitude, but not necessarily. They could have different magnitudes. So mathematically, what we're looking for is the point where delta f, or del f, is equal to some constant lambda, and we put a negative in front just by convention, okay, times the gradient vector of g. One is a scaled version of the other, but they're parallel. Okay, if lambda is a positive number, then the gradient vector of g points in 180 degrees opposite direction of gradient of f. If lambda is a negative number, then the gradient of g points in the same direction as f. But their magnitudes might be different depending on the magnitude of lambda. Okay, so this is the big result. So we're looking for those points where the gradient vector of f is equal to sum minus lambda times del g. And lambda is what we call the Lagrange multiplier. Okay, we multiply the gradient vector of g by the Lagrange multiplier. Lagrange was some guy who lived back in the 17 or 1800s and thought this up. Okay, really, we also call it a nuisance parameter. Okay, because now we've added an extra unknown. We don't know what lambda is. Okay, so we actually have to, well, we don't have to solve for it, but we need basically three equations, because If our function f of xy is z is equal to a function of xy, we're looking for values for x and y that give us a maximum subject to this constraint, g of xy is equal to c, some constant, okay? So x and y are two unknowns. Now we've got a third one, lambda, which means we need three equations, because we got three unknowns. Okay, well, what are the three equations? Well, if, what should I write next here? Yeah, I kind of skipped over that part. No, we can just write it from here. So if we take this equation now, what is the gradient of f? Well, it's a vector. It's the partial derivative of f with respect to x, partial derivative of f with respect to y. Okay, is equal to minus lambda times the gradient of g. And the gradient of g is the partial derivative of this function g with respect to x, partial derivative of g with respect to y. So for that equation to be true, what does it mean? Well, it means that the x component of the vector on both sides has to be equal, right? So that means we can write the partial derivative of f with respect to x has to be equal to minus lambda times the partial derivative of g with respect to x, and the partial derivative of f with respect to y has to be equal to minus lambda times the partial derivative of g with respect to y. Okay, for that equation to be true. Or if I rearrange each of those a little bit, I write it this way instead: partial derivative of f with respect to x plus lambda g with respect to x is equal to 0. F with respect to y plus lambda g with respect to y is equal to 0. Okay? So that's two of the equations I need. I've got three unknowns, x, y, and lambda. So that's two equations. What other information do I have? What could be my third equation? It's just our constraint. We also know that whatever the x and y values we're looking for have to satisfy the constraint equation, right? The constraint equation means I got to be somewhere on this line, on this level curve. I can't pick an xy over here or xy over here. Xy have to be along here. Okay, so that's my third equation. The first two equations come from the fact that these two gradient vectors have to be parallel, but not necessarily of the same magnitude or direction. Well, the direction has to be 0 or 180 degrees, difference between the two. Okay, that's where two of my equations come from. The third equation is just this one. So now I've got three equations, three unknowns. So that'll allow me to find x and y where f is maximum or minimum subject to this constraint. Sometimes we put this all together into one equation called the Lagrangian. So it's a function of three things, x, y, and lambda. And it's just going to be equal to this. Okay, and we're looking for xy so that the gradient of this thing is equal to 0. Okay? And this thing contains all the information we have. The objective function we're trying to minimize or maximize, and the constraint equation, and it's also got this lambda in it. Everything up here, all of this is the same thing as finding this. So if you took the gradient vector of this, okay, it's a function of three things, so you'll get a three-dimensional vector, and you set that equal to 0, Well, you'll have three equations, an x, a y, and a z, an x, a y, and a lambda component. And for that gradient vector to be equal to 0, each of those components have to be equal to 0. It'll give you these three equations. Okay? If you do this, you take the partial derivatives of this with respect to x, y, and lambda, you'll get these three equations. Okay? So that's all we have to do. All right, so let's look at an example where we don't use the Lagrangian right away. Just to drive home exactly what we're trying to do here. Say we've got an objective function f of xy is equal to x squared plus y squared. And we've got a constraint equation, y minus x is equal to 2. I'm going to go over this pretty quick because what I really want to do is the next example with a Lagrange. Okay, so what is x squared plus y squared is equal to z? Okay, I could write z is equal to a function of xy. What is z is equal to x squared plus y squared? I keep telling you, you've got to be able to imagine some of these simple surfaces. Okay, its level curves would be circle, but in 3 dimensions it would be not a cylinder. When x and y are equal to 0, what is z? 0, right? When x and y are something other than 0, what is z? A positive number. Okay? So that means z is never negative. Okay? And if you look at the level curves of this, don't do that. Right? Which say z is equal to 1 is equal to x squared plus y squared. Z is equal to 2 equals x squared plus y squared, right? 1 equal to x squared plus y squared is a circle in 2 dimensions. 2 is equal to x squared plus y squared is a circle with a bigger radius. So the level curves would be concentric circles in the xy plane, centered at the origin. So in 3 dimensions, that would give you a paraboloid, right? Down on the xy plane is the bottom of the paraboloid, and then it gets bigger and bigger and bigger. The other way to think about it is, what if I go back here and I make x equal to 0? I get z is equal to y squared. That's an upward paraboloid in the yz plane, right? So I've got a paraboloid. My function is a paraboloid like this, okay? Take a parabola in 2 dimensions and spin it. You get a paraboloid, okay? That's what my objective function is. Obviously, the minimum of that would be when x and y are equal to 0, okay? I'd get z is equal to 0, the minimum. But that doesn't work for the constraint equation, because x equal to 0 and y equal to 0 does not satisfy my constraint equation. So I can't choose x equal to 0 and y equal to 0. So that means there's some other point in the xy plane that corresponds to the minimum for this function that corresponds to this. Okay, well, if we would sort of draw this. First, I'm going to draw my objective. No, let's draw the paraboloid first. So it's going to look, this is x, this is y, this is z. And so we've got our paraboloid. It looks like this. Okay? And again, if I ask you, what's the minimum of that? You'd say, well, right down here. X equal to 0, y equal to 0 gives me a minimum value of z. But that doesn't fulfill our constraint equation. What is our constraint equation? Our constraint equation is y minus x is equal to 2. Well, that's a straight line in the xy plane, right? When y is equal to 0, x would be equal to negative 2. Okay, yeah, I should have drawn. Can I flip this? It'll make it easier, sorry. I'm going to make that the positive x-axis. So that means this is the negative x-axis. And this is actually the y-axis. Okay, that would still be a right-handed 3-dimensional coordinate system. It's just going to make it easier to draw. Okay? But the paraboloid still looks like that. Okay, so let's draw our constraint equation on here. It's a straight line in the xy plane. When y is equal to 0, x is equal to -2. Okay, well that would be right about there. X value of -2, y is equal to 0. When x is equal to 0, y is equal to 2. That would be right about there. Okay, y of 2, x is equal to 0. So that means my straight line just connects those 2 points like that. Okay, so that means I'm looking for the minimum value on this surface, the minimum z value being on this surface if x and y are constrained to be on this line. Okay, so where is it going to be? You tell me. Tell me when to stop. Oh, that wasn't very convincing. I'm going to keep going. Where am I on the minimum value of this as I travel along here, if I'm looking straight above? Right there. Right? It's going to be right about there. Okay? So that's going to be right there. Okay, the way I can find that is I know. So let's do that again, but this time, as I walk along here, again, I've got a chain connected to my top of my head, and it goes to the foot of somebody walking on the surface of that paraboloid, and he's always directly above me. As I'm walking along this line, he's walking along the surface. Well, what's that going to look like? It's going to look something like, this is going to be his path, right, along the paraboloid. He's directly above me, walking on the surface of the paraboloid as I'm walking on this line, right? Well, when I get here, the distance between us is going to be the shortest, right? That's when he's at the minimum on that paraboloid. And he's always directly above me as I'm walking along this line. Okay, well, what's special about how the function changes as I'm moving along here? What happens to right here? He's not going down, he's not going up. So that means the derivative of this function at this point is equal to what? Sorry, there. 0, right? So df by ds at the point I'm looking for is equal to 0. And remember, df ds is a directional derivative, okay? It's equal to the gradient of f at the point I'm looking for dot u hat, where u hat is a unit vector pointing along here. That's my u hat. Okay? As I move in the xy plane along that straight line, I'm looking for the point where df by ds, or where that function isn't changing. That was just the directional derivative we talked about in the last couple of lectures. Okay? So that's what I'm looking for. I'm looking for that point there, where that directional derivative due to that u hat is equal to 0. Okay, well, to do that, we need u hat. Well, we can find u hat. We can, right, we've got 2 points on this line. This one is 0, 2. This one is -2, 0. We've got 2 points on that line. We can draw a vector between them, divided by its magnitude, and you've got u hat. Okay, that's something you should be able to do, no problem. I'm just going to write that down. It's 1 over √2. -1, -1. I've chosen u hat in that direction. Doesn't matter. I could choose u hat in the opposite direction. Shouldn't matter, right? Whether I'm changing x and y in this direction to see what happens to f, or if I'm changing x and y in this direction to see what happens to f, I should get the same result. I'm looking where the change in f is 0. Okay, well, then you can do the, what should I write here? Okay, what's going to be special about the gradient vector of f at this point? If I would draw the gradient vector of this function in the xy plane, right, because z is equal to a function of xy, the gradient vector will be a 2-dimensional vector. I can plot it in the xy plane. What will it look like right here? It's going to going to be perpendicular to u hat, right? At this point P0, that's point P0, the point I'm looking for. Okay, at point P0, I'm looking for that gradient vector, and it's going to be perpendicular to u hat. Well, I can calculate the gradient vector, easy enough. Right, the function was x squared plus y squared, so that's going to be 2x, 2y. So now I need del f, I need this, 2x, 2y, dot 1 over root 2, minus 1, to be equal to 0, right? The dot product between del f and u hat has to be equal to 0 because I reasoned back here that those two have to be perpendicular to each other at this point. So that means their dot product has to be equal to 0. That'll give me two equations, two unknowns. I solve for x and y. I get P0 is -1 and 1. Oops. Don't do that. Sorry. Okay, so I got a fancy picture that we can look at. Okay, so here's my paraboloid. It's this surface here. Here's my constraint equation in the xy plane, that line that we drew, okay? Here's my path along the surface, or not my path, but the guy who's connected directly above me. As I'm walking along this line, he's walking along this surface, he's going to follow this path if he stays directly above me as I'm going along here, okay? And we found it was this point here at y, well, they've got t and t plus 2, but it's x and y. 1 and 1 are the coordinates of this point here in the xy plane that we found. Or we found 1 and -1, didn't we? Yeah, so these are kind of screwed up, these axes. Okay, but the important thing here is that it's tangential to this level curve. Well, what level curve is this? Well, it's x squared plus y squared is equal to some z constant. Okay, and if you put x -1 and y +1 into our function, z is equal to f of xy, which is equal to x squared plus y squared. I get what? I get -1 squared plus 1 squared. So obviously it has to be equal to 2, right? So this is for a z value of 2. So this level curve is equal to x squared plus y squared is equal to 2. Okay? So we found it without the Lagrange multiplier. It'd be very good practice for you now to do this with the Lagrange multiplier. Make sure you get the same result. Okay? And it's just positive. You got three equations. X plus lambda g x equals 0. F y plus lambda g y is equal to 0, and g of x, y is equal to c, right? That last one in this case is just going to be, what was it equal to? Y minus x is equal to 2. This guy here is y minus x is equal to 2. Okay, and g of x, y is equal to y minus x. So you find the gradient of f, find the gradient of g, right? You plug everything into here. You got this equation, which is just this. 3 equations, 3 unknowns, x, y, and lambda. Okay? All right, we'll see you on Friday.